Hello everyone. This video will act as the first experimental video for Organic 1 Lab CH4511. And so in this experiment, you'll be testing melting points. All right, with this experiment, there are 4 parts typically to this experiment, but the experimental video that you may see will actually exclude part B. In determining the melting point of an impure substance, where you actually will take the pure and then you'll deliberately add a different compound to it to see what happens in the digimelt. But we're going to have, let's see, 4, 5, 6, 7 compounds that could possibly be tested. You're going to be focusing in part A, you're actually going to just look at 3 of these 7 pure compounds, and you're actually given you're actually given the for the compound name, you're given the literature value for the melting point, and so you're going to see what the melting point range, all right, and I can't stress that enough, melting point range that can be observed in the digimelt for the 3 possible structures shown here or listed here. All right, and so you can see they all do kind of have a large difference, somewhere between 20 to 30 degrees Celsius difference between them. So each of them can be easily distinguished from one another in the digimelt, looking at when they melt. Okay, and so like I said, part A, you're just going to take 3 of these you're going to see 3 of these knowns being melted, and you're going to compare the range that you get for melting. So when it starts to melt to when it has completely melted, right? And so as we know, when something melts, it transitions from a solid phase to a liquid phase. So you'll see some of the solids start to melt, and then once it's all liquid, then you'll have the end of your range. All right, and then for that, you will also need to calculate the percent difference in error. So to do that, you're going to take the literature value, what's up here in the table, and then you're going to kind of take the median value or the middle value for your range as your experimental. Okay, for the experiment video, part B will be skipped, but really this is just to check and see what happens to the melting point or melting point range for one of those above mentioned known compounds once you have deliberately put some impure stuff in there, and we'll actually talk about that in a second. All right, and then for part C, you're going to have an unknown, and so you're going to determine the melting point range for the unknown. And then in D, to help you identify the unknown, right, because your unknown is going to be one of these 7, and so to help you identify the unknown more precisely, you're actually going to take that unknown, and then you're going to mix it with the 3 closest compounds that have a melting point. So say, for instance, if you saw your unknown, let's say you suspected it was benzamide, and it melted at, say, 134 degrees C. So what you would do is you would take one sample where you take your unknown and mix in a little bit of acetanilide. That would be your first one. Your second one, you would take your unknown, mix it with a little bit of benzamide, and that would be your second sample. Your third sample, you take your unknown, and then you'd mix it with a little bit of salicylic acid. And so what you're going to do is you're going to melt all 3 of those, because then what you're going to have is a mixed melting point. Okay, and so what you should see is either you're going to see a huge decrease in the melting of your unknown, or you're going to see some solid kind of stay behind as one piece of the puzzle melts, right? Because now what you've done is you've taken it to where each one of your samples is a mixture of 2 compounds, right? It's your unknown plus one of these 3, right? So, and you can actually clearly see that in the experimental video. All right, and so that's just going to help you identify the unknown to be a little more precise. Now, when generating waste, it's very important to know where waste would go. So for this particular one, mostly what you're looking at here is solid waste. And so that's any leftover solid compounds. There should be a Ziploc bag in the fume hood that's labeled melting point solids or melting point, and that's where you would dispose of all of those in that Ziploc. And then lastly, you're using capillary tubes in they're little tiny little glass tubes. You're using those in the Digimelt to help you determine the melting point, and so for that, they're made of glass, so you would actually dispose of those in the broken glass box. Okay, now, with that, to kind of understand what's going on here, we need to discuss a little bit about technique, like what's going on. So, not only do you need to kind of go through and look at the experiment for melting point, you need to also jump in the appendix to determination of melting points. All right, and so all of this kind of goes a little bit more in detail about melting points. So for instance, what is the melting point? Right, we've kind of already said that. It's the temperature at which a substance will convert from solid to liquid phase. All right, and typically they do put in there that's at 1 atmosphere of pressure. All right, so if the environmental pressure is different than 1 atmosphere, you can see shifting in your melting point temperatures. Okay. And melting point is one of many physical properties that a compound has. Right? So physical properties are those that are just intrinsic to that compound, and so they help in describing and identifying the compound. So besides melting point, some other physical properties would be boiling point. Right? When you go from a liquid to a gas, the refractive index. Right? That's how it bends light. The density. You're all familiar with density. And solubility. So how well does it dissolve in a given solvent? So solubility, you could look at how well it dissolves in water versus how well does it dissolve in an alcohol versus how well does it dissolve in hexane or propane or something like that. All right. So all of those are great examples of physical properties. And so to be as precise as possible when you are looking at your melting point ranges for these known compounds, you do want to gradually heat the sample. All right, so that means you don't want to just ramp it up really fast. You kind of want to take your time. And so one of the things to make sure of here is your melting point range for a very pure substance usually has a melting point range that's about 1 to 1.5 degrees Celsius within the literature value. Okay, and so if you ramp up your melting speed on your Digimelt too fast, instead of it could be a pure sample, and so instead of it having a melting range of 1 to 2 degrees Celsius, it could have a melting range of like 5 to 8 degrees Celsius because you're just heating it way too fast. And so that's something to be aware of. Now, also, in terms of having compounds that are impure, what are some things that we can see? Well, if you have an impurity, typically what winds up happening is that you see a decrease in the melting point of that pure solid. All right, and so, like for instance here, if we compare two solids, solid A and solid B, all right, if you had pure A, meaning no B, right, if you had pure A, it would have this melting point. And then as you add more and more impurity of B, you see the melting point begins to decrease. Decrease. And then you hit this point right here, what's called the eutectic point, and I'll talk about that in a second. And then as you go to more and more B, you can see it increase yet again. Okay. Now, so what you see is a melting point depression typically when you have an impurity present in your solid. Okay. Now this eutectic point, and this eutectic point doesn't really make sense until you start talking about what you visually see. So sometimes when you have your little capillary tube, let's say it's got a mixture, it's got impurities. So here's my capillary tube, right, and it's going to be in the Digimelt. And so let's say you've got a solid, right? So all of that's a solid. Okay. Now it doesn't really look that great as a solid, but it looks homogeneous. Let's just say it looks like a regular white powder, but there's both compound A and B present here. Now, what winds up happening, A has a much higher melting point than B. And so what's going to wind up happening, let's say that it melts at 104 degrees C, while this one melts at 80 degrees C. So what's going to wind up happening here, let's say as you reach 80 degrees C, what you would see is B would melt, but A would still stay as a solid. So you'd actually see a mixture of a liquid and a solid at roughly 80 to 100 degrees C. But then once you hit 104, right, that's when you're going to start seeing nothing but a liquid. So you got nothing but solid below, say at room temperature, right? And then at 80 degrees C, you're going to see mostly a bunch of solid. The circles will be my solid, and then you'll see like liquid and solid together at, say, approximately 80 degrees C. Okay, so liquid plus solid. And then, of course, definitely at 104 degrees C, you're going to see nothing but liquid at 104 degrees C. Okay. Now, that is if you have a ratio of A to B that's not at the eutectic point. All right, so at the eutectic point, what winds up happening is within a given ratio of A to B, you don't at a given temperature, you'll actually see nothing but liquid at a temperature that's lower than the boiling point for both of these, for both A and B. So you could actually see, like at 60 degrees C, you could see this nothing but liquid if you have a very precise ratio of A to B. All right, that's the eutectic point. And so that's what this is kind of saying here. So when you have about 60% B, that's at 60% A. Yeah, so when you have about 60% A and 40% B here, you're going to see a liquid at this melting temperature, right? But if you were to knock it off just a little bit to where you had, say, 55% A and 45% B, you would see at this temperature, you wouldn't actually see liquid. You would see a solid and liquid together at that given melting temperature. All right. Anyway, so the eutectic point is very rare to see. All right. So it's not really something you're going to have to worry about. But the thing that you do want to be aware of is a mixed melting point. All right, because as we said in part D, you're going to be incorporating the use of a mixed melting point to help you narrow down your possibilities of unknown compounds. All right, and so what you're going to do, for instance, for a mixed melting point, all right, what we see happening whenever we have an impurity present, we see melting point depression, right? So the melting point of our solid goes down some. All right, so in a mixed melting point, you can take two substances, say what you believe it to be, right? Say it's your two choices of whatever it is, right? So what you would have is, so for a mixed melting point, you would have, say, you took the melting point of an unknown X. We don't know what that is, right? And let's say you recorded a melting point range of, actually, and I'll use the values from the manual, from the experiment. So let's say you have a melting point of 114 to 117 degrees C. All right, so when I looked at that unknown, that's the melting point range I got. And so what I said was, all right, well, when I look at my manual, right, in my list of compounds, I see, let me go back to my table real quick. I see here that around 114, it would be acetanilide, right? So then I'm going to prepare 3 samples. Right, and for those 3 samples, let me move this over here. For those 3 samples, I'm going to have sample number 1, which will be unknown X plus a little bit of, and I look at my table here, hang on. So I think it's acetanilide, right? So what I'm going to do is I'm actually going to look at these 3, right? The one that has the melting point below it, right at it, and above it, right? So I'm going to have unknown X plus acetamide added in. Sample number 2 would be unknown X plus the acetanilide, TANIL. And then sample number 3, unknown X plus benzamide. All right, so this would be my 3 samples. All right, and so what I should see if unknown x actually is this, right? If unknown x and acetan line are the same thing, what I would see at roughly, so let's say, if I look around acetamide melts at 82. So at about 82 degrees C, for this sample, I would see a solid and a liquid. Okay. And then for acetanilide, at approximately 114 degrees C, I would see nothing but liquid. Because remember, if unknown X is acetanilide, then that means I haven't spiked it with an impurity. It should stay a liquid, right, at that melting temperature. And then for this sample, at 114 degrees C, I should see both a solid and a liquid. Because benzamide melts at approximately 130 degrees C, right? So that's what I would see there, give or take. And this would be for your mixed melting points. Okay. All right. And then lastly, just to kind of familiarize you with what you could possibly see here, jump to page 140. You will be using a Digimelt apparatus here, so it's just a digital melter, right? And so it has kind of this general layout where you have a start temperature, you have a stop temperature, and then you have what's called a ramp rate. So, for instance, if you were looking at acetamide, it melts at 82. So what you would want to do is you would want to have a start temperature where you're heating the sample, say at 70 degrees C, right? So approximately 10 degrees C below it. And then you want your stop temperature to be roughly 10 degrees C above the melting temperature. So you have a nice big range. And actually, to be even better, you would want to say about 15 to 20 degrees below and above, right? So if your melting temperature was 85, so if your melting point was roughly 85 degrees C, then the range, it was 85 degrees C, then the range you would want to look at in the Digimelt would go, say, 65 to 105 degrees C. All right, that would be the best range to look at there. And then the slower the ramp rate, the more accurate your data will be. And so really I kind of say you don't want to go more than 5 degrees C per minute if you want to be very accurate. And I believe, I can't remember all of the different rates that it has, but I think it has like 5 degrees C, 10 degrees C, and 20 degrees C per minute. And so you can use it with that ramp rate button right there. And then there is a readout here. It's a nice little red digital readout that you can see. So you'll be looking in a window to see if your solid has melted, but then you're also going to have to check this readout right here to see at what temperature it's melting. Okay. All right. So that should at least get you mostly prepared for what's about to happen. All right. Good luck.